Hi everyone, welcome to Optimization for Deep Learning, or Opt4DL for short, where in this course the goal that we are pursuing is to leverage optimization theory and algorithms to understand deep learning. Notably, we want to understand how we can build deep learning models to learn from data, why deep learning models are successful in doing what they are designed to do, and how can we provide formal guarantees on their performance as well as any other criterion that we may have in mind. So in this lecture, we're going to provide an introduction to the course and essentially motivate the course. As you can see in the title, we have two main keywords here. We have optimization and we have deep learning. So what I'm going to do, I'm going to first talk a little bit about optimization and a little bit about deep learning and see how we can merge these together to achieve the goals that I mentioned, notably understanding deep learning. And I want to essentially motivate the thesis that optimization is a very useful and handy tool when it comes to understanding deep learning models and designing deep learning models. All right, so introduction to the course. So as I mentioned, the first keyword that we have is optimization, okay? And by that I mean mathematical optimization. What's the goal of optimization? So the idea at a high level is that we want to select or identify the best element, let's say from a set of alternatives, with respect to a criteria, okay? Many times in optimization, the goal is to minimize some cost or loss function, okay? And an example of this is in machine learning, which is our main motivation in this course, where we want to, let's say, minimize certain loss function to ensure our model provides the best fit to the data, okay? Alternatively, you can talk about maximization, and these are equivalent in some sense. That means that if I give you a cost function, I can define its negative to be some reward function or utility function, right? So in a lot of applications, we are interested in maximizing some reward function or some utility function, okay? So the problem that we're going to have, instead of minimizing f, we're going to maximize u. So an example of this is when we have, let's say, an application of reinforcement learning, where our goal is to design an agent that can perform a certain task, okay? Another example is portfolio optimization, right? So from a given set of stocks or resources, we want to select the ones that result in the highest profit, okay? Now, here, f, as I mentioned, is our loss function or cost function. U is our utility function. W is essentially our decision variable that we are optimizing over, okay? And x here is essentially our set of alternatives. So this condition or constraint that says W must belong to x means that the solution that we're going to find is should satisfy certain constraints in order to be feasible, okay? I would say that for most of the topics we're going to talk about in this course, we have problems where the mathematical optimization problem is an unconstrained problem, meaning that x is essentially just the whole Euclidean space, RD. All right, so this is the goal of optimization, and we are concerned with modeling, algorithms, and assessment, and all of these are pertinent to machine learning, therefore to our course. So when I say modeling, that means that I describe a problem to you, and in order to find a solution to that problem, the first thing you need to do is to model it as an optimization problem that could be solved efficiently, Okay, so that is, I would say, an art by itself. Another thing that we are concerned with in optimization is design of algorithms. When I give you a mathematical optimization problem like this, what are the best algorithms in order to solve this problem? And by best, we typically mean algorithms that are the most efficient. And finally, assessment. So one thing that optimization can do is to provide formal guarantees on the quality of the solution, right? So I can, for instance, say that which properties the cost function f, for instance, should have in order for a certain class of algorithms, in order to, such that certain class of algorithms can provide a good solution efficiently, okay? So all of these of our importance in optimization. And I would say for the most part, we're going to talk about algorithms, right? So that means that what are algorithms, what are some algorithms that we can design and leverage to train deep learning models, right? So what can we say about the quality of the solutions we find using this algorithm? So that's the topic of assessment. Okay, so that's a brief introduction to optimization and the goal of optimization. Now let's move on to our next keywords, deep learning. Okay, so what is deep learning? And to define deep learning, I'm going to provide two definitions that are, one of them is basically, I would say, a universally accepted definition that I have here. Another one is by one of the prominent researchers in the field of deep learning that we're going to see. So the first definition says that deep learning is a class of machine learning methods, right? So this is another keyword that we're going to define in the next lecture. For the time being, you can imagine that machine learning means learning a model from data or designing a model from data, okay? So deep learning is a class of machine learning methods based on artificial neural networks or ANNs. And what are these? So these are basically models that are designed based on biological neural networks, right? That have neurons receiving signals, processing those signals, and passing them along to the next neurons. So based on this concept, we can design a class of models that we refer to them as artificial neural networks that is of essential importance in deep learning. So deep learning, a class of machine learning methods based on artificial neural networks that enable learning or identifying useful patterns from data and applying those patterns to new data. This simple image sort of shows the procedure. So let's say we want to design a model that can classify whether a specific image is an image of a car or something else, okay? So what we'll do, we gather a large collection of images that are car and not car, okay? So that's the first step. We define a certain artificial neural networks following a specific architecture, and this is something that we're going to talk a little bit in the course as we move on. We're going to design training algorithms and feed these training data to the model to tune the parameters of the model, okay? And once the training is done, we have learned potentially some useful patterns such that our model is now able to distinguish between images that are car versus images that are not car. Now, ideally, what we are hoping for is to not only perform well on the collection of images that we've used to train the model, but also perform extremely well on the images or the data that the model has not seen during the training phase, okay? So that corresponds to applying the patterns we've learned from the data to new data that we haven't seen, okay? And deep learning has been extremely successful It has found many success in many application domains. And most recently and most notably, we have seen success stories in the domain of generative AI. For instance, we have chatbots that you may have interacted with, such as ChatGPT, Claude, etc. So these are things that you can give them a certain prompt, certain command, and the model is going to respond to you or generate some response to your query. Okay. We also have models that are extremely successful in terms of generating, let's say, images, right? So such as Stable Diffusion, right? So you give it a command and ask you to, for instance, generate the image of a specific cat breed or dog breed, and the model is extremely successful in doing that. And there are a lot of other, again, applications that the deep learning models have been really successful at across science and engineering. All right. Now I'm going to talk about sort of, if you will, a related but a slightly different or technical definition of deep learning, and as I mentioned, provided by one of the pioneers in the field. Okay, so let's see what this definition says. So deep learning, or DL, is basically constructing networks of over-parameterized modules. Okay, so this you can think of as designing a very, very large scale artificial neural network and training them from examples. So this means that this large over-parameterized model that you've defined, you want to fit it to the training data. Okay. Now here's the interesting part that I'm going to leverage as motivation for this code. Using gradient-based optimization. Okay, so therefore, the choice of the training algorithm is also essential when defining deep learning. Okay, so and this shows the crucial role of optimization, or if you will, the right kind of optimization in making sure deep learning models work, and also in trying to understand why and how these models work. Okay? And I would say the key word here is the right kind of optimization, right? So gradient-based optimization. That's why in this course we're going to pay a lot of attention and focus on certain class of optimization algorithms that leverage this gradient information. All right. Now, why optimization for deep learning? Okay, I would say there are at least two main reasons. The first reason is that was somehow reflected by the definition we saw in the previous slide. The first reason is that the learning in deep learning and machine learning boils down to optimization problems. Okay, so that means that if I want to train my model, I'm going to have to solve an optimization problem. Okay, so if I want to understand why my model is able to fit the data, why my model is able to generalize to unseen data, we have to understand these fundamental optimization problems. And naturally, optimization theory has a lot to say about that. The second reason is that there are a lot of mysteries in getting deep learning models work, okay? And this applies not only if you want to train a model from scratch, but also if you have access to some model that you want to fine-tune to your specific needs, okay? So there are a lot of mysteries and challenges involved in this process. Now, given that training the model or fine-tuning the model involves solving optimization problems, the right kind of optimization may lead to developing an understanding of these mysteries and hopefully helping in demystifying them. Okay, now I'm going to talk a little bit about these two reasons. First of all, the intimate connection of learning and optimization. Okay, So I mentioned that when we talked about training a model, essentially fitting the model to a training data, we have to solve an optimization problem, okay? Now, a little bit more mathematically, this optimization problem is gonna look like something like this. We still want to minimize a loss function. Here, I denote that by f. But the loss function is not arbitrary. It takes many times a specific form. In particular, many times, the loss function can be thought of as being the average of some other functions. Okay, so here in this case is 1 over n sum over I of these fi's. Okay, now what are these fi's? Fi is essentially going to determine how the model W is going to fit data I. Okay, so in particular, I have a data set of, let's say, n samples. Let's say I have xi, yi, xn, yn, and this is something we're going to talk about in our next lectures a little bit more deeply. So, for instance, xi could be thought of as a collection of pixels. Yi could be thought of as a label that says whether this image is an image of a car or not. Okay, and Fi captures how a model W or how a specific neural network with parameters W can fit the IS sample. Okay, so this is a specific structure that you can imagine for a lot of learning tasks in optimization, in machine learning and deep learning. Okay, so n, as I say, is the size of the training data, and the challenge here is that n is not a small number. It typically, in a lot of cases, is orders of millions or even billions. Okay, so we have billions of data points to fit. D is the number of parameters. Okay, so this is the number of tunable parameters that are that we have, or the number of parameters that we have to again optimize in order to find the best model. Again, the challenge is that the model size could also be very, very large, even up to order billions. Okay, and in fact, the models are over-parameterized, as we saw in the definition of deep learning, and that means that sorry, I have a typo here. That means that D is larger than N. Okay, so we have more parameters than data points. Or in other words, we have more unknowns than knowns. That means that there may be multiple solutions or multiple optimal models. Okay, and as a result of this, these complexities, the loss function that we have to deal with is non-convex. Okay, we're going to talk about convexity and non-convexity in the next lectures, but for the time being, you should think of a convex function as a function that is very, very nice and easy to optimize, something like the one that we have on this side. So this is convex. As you can see, the function is curved very nicely upwards, and there is only one solution here, unique solution. On the other hand, the function that we have to deal with in machine learning and deep learning, when we want to, again, fit a specific model to data, are non-convex, means that the landscape is full of hills and valleys, right? And there may be a lot of solutions. So we are not guaranteed to find the best solution, right? So, and in fact, in many cases, it matters where you initialize your algorithms, because in a lot of cases, we have local algorithms, right? So, for instance, in this figure, if I start, let's say, my algorithm here, this is the solution that I'm going to find. If I start my algorithm here, I'm going to find another solution, right? And these solutions are not the same. One could be better than the others, right? And to understand which one is better or how we can find the best solution, again, we have to notice that we are solving an optimization problem. Therefore, we may want to leverage insights from the field of optimization theory. All right, so that's a little bit about the connection between learning and optimization, right? And essentially one of our motivation for this course. Another one is on the existence of certain mysteries when training deep learning models. And I'm mentioning a couple here, but there are a lot more mysteries. And there are a lot of things we still don't know about deep learning models. Okay, so the first mystery is why/how ADAM works. What is ADAM? You might have heard ADAM, and that's nothing but an optimization algorithms that is used extensively when training deep learning models. Okay, and it has received a lot of attention, and it is, I would say, very, very successful many times when training sophisticated deep learning models. Unfortunately, when the paper came out almost 10 years ago, later on people noticed that there was some mistakes in the theoretical guarantees that they would provide. And in fact, sometimes certain variations of this algorithm may even fail to solve easy problems, such as convex problem. So here is what is meant to show the failure of ADAM for a simple problem. Essentially, you should be able to find a very good solution, but given that ADAM has some problems, there is a gap. Okay. So a mystery is that why ADAM works, or how ADAM is able to work very successfully when training complicated deep learning models, but it may fail for some simple problems. Okay? And again, to understand this mystery, we should hopefully leverage ideas and insights from optimization theory, because at its core, ADAM is an optimization algorithm. All right. The second mystery is about the central role of overparameterization. Okay. So as I mentioned, almost all of the deep learning models that we currently have and are leveraging in various applications are overparameterized, meaning that they have more parameters than data points. Okay. And this is a little bit contradictory to the traditional wisdom that we have from machine learning theory, because traditional machine learning seems to require the total number of learnable parameters, to be less than n, okay, the number of data points. And the idea here is that if d is large, the model becomes too powerful and may overfit the data. So that means that we are not going to be able to learn useful patterns from the training data and leverage it later on to new data. We're going to fit the training data very well, but the patterns are not applicable broadly. Okay. Despite this, in practice, as I mentioned, d is typically much larger than n. Okay. And the observation that we have is that not only this condition or this regime is going to help us to train the models better, meaning that fit the training data better, but also in this regime, the models tend to even generalize better, meaning that they can apply the patterns that they learn from the data to new data and still be successful. Okay? So therefore, the mystery is that from all of these available solutions, remember that when d is larger than n, that means that we have more unknowns than knowns. So there are multiple solutions. And from all of these, magically, the deep learning model finds the one that is doing great. Okay? And this is sort of a figure that depicts this phenomena, and we're going to get back to it later on in the course. So here we can see what we expect from the traditional machine learning model. Essentially, that says that when we talk about the training error, as I increase the model size, the training error is going to decrease until a point such that after I increase the model size, the test error has to go up due to overfitting. But this is not the phenomenon that we are observing in practice. What we are seeing in reality is that as I start to increase the size of the model, the test error is going to go down, then it's going to go up, but there is a certain point after which, as the model becomes more overparameterized, in fact, the test error is going to start going down again, such that for a very, very large model, I can actually get a better performance. So this is the performance gap between an underparameterized model and a very, very large overparameterized model. So in fact, overparameterization, despite the conventional wisdom, seems to be helpful. Okay, now this is a mystery that we want to develop an understanding for. And again, given the connection between learning and optimization, we should expect optimization to be able to help us with that. All right. Now, another question that I want to answer is why developing an understanding is essential. And my answer is that deep learning is and probably will continue to be a useful tool in many fields across science and engineering. So therefore, this is a tool that we're going to apply, and it's good to have a good understanding of this tool, okay? And it's not just that we have developed models that can be applied universally. We always have to deal with more than one task, more than one data set, right? So we have always new tasks that could benefit from deep learning. We can always expect to have new data sets that we have to crack, right? So therefore, we have to develop an understanding that for a new task or for a new data set, should we expect a deep learning model, a specific deep learning model to work, and why? But beyond this, deep learning training is actually very, very costly. So, and the current success is reliant on expensive hardware and high energy consumption. So here's sort of a figure trying to show that what's the carbon footprint of training a certain deep learning model. For instance, here we have a specific architecture transformer, and as you can see, its carbon footprint is significantly large, and in fact, it's significantly larger than the carbon footprint associated with life of a human being. Okay, so given that this training is very costly, then we should try to find more efficient or eco-friendly, if you will, approaches to train these models, right? And given that training is, again, essentially solving an optimization problem, optimization is going to be a handy tool to perform this, okay? And finally, there are societal concerns and implications of deep learning, and it is important to study this and develop approaches to mitigate them and resolve them, okay? And to do that, naturally, we have to have a certain level of understanding of deep learning models and practices. All right. Now that we talked about the connection between optimization and deep learning, and we talked about the importance of developing an understanding of why and how deep learning models work, another question is why the right kind of optimization may be helpful. And I talked about this extensively, that optimization and learning are entwined. There is an intimate connection between them. optimization is one of the main pillars of successful deep learning. It's not the only one, but it's certainly of essential importance. And as we talked about in the previous slides, modern optimization theory can provide actionable insights about complex, non-convex loss landscapes that we deal with in deep learning, and their implications to both convergence, and by that I mean how well I can fit the training data, and generalization, how well I can apply the patterns that I learned during the training to unseen data. Okay. All right. Now, what are our main goals in this course? So, one of our goals is to learn about learning techniques, training algorithms, optimization algorithms, and potentially the knowledge that we gain in this course could be leveraged to develop new algorithms or understand or develop knowledge that we currently don't have about the existing algorithms. We're also going to discuss optimization for deep learning theory, methods, and heuristics, right? So that means, again, analyzing training algorithms, understanding algorithms that are based on mathematical principles, and also trying to learn about certain heuristics that are arguably essential when training a deep learning model and trying to understand them, right? We want to pose why questions. Okay, so why a specific method is able to, let's say, work in certain scenarios, why it's not able to work in other scenarios. We want to discuss what we already know and what are some things that we need to know, okay? And how we can approach these questions. Later on in the course, we're going to talk about how we can leverage these tools and these methodologies for resource-efficient deep learning training. And finally, our hope is to discuss some pertinent practical and societal concerns and see how we can integrate them with our optimization, our base optimization methods that we use when training deep learning models. All right. Now, I want to talk a little bit about myself. So I'm Abulfazl Hashemi. I'm an assistant professor at the Elmore Family School of ECE at Purdue University, and I've been here since fall 2021. My research goal is actually intimately connected to optimization. I hope to contribute to the advance of the field of large-scale optimization. That's essentially a kind of optimization that deals with problems of a very large scale. Could be, again, mainly motivated by problems that we deal with in machine learning and deep learning. And my goal is to provide actionable insights from this perspective to innovate multiple domains within machine learning and AI. So, for instance, robustness, developing equitable algorithms, etc. And recently, my research group has focused on applications to federated learning or collaborative learning, applications of deep learning to medical image analysis, next generation of manufacturing, and also cyber-physical systems. Right. With that, next lecture, we're going to talk a little bit more about optimization. Basically, we're going to provide a very short course, an introduction to optimization, as well as machine learning. And we're going to progress to other topics in the next lectures. Thank you.